In this tutorial, we're going to talk about E2 stereospecific elimination reactions as well as stereoselective reactions. In the example we have here, we see that we have a bromine group on the alpha carbon as well as a hydrogen that is on a dash. That is an indication that as far as we have only one hydrogen on the beta carbon, we're going to get only one product. And that is what we call stereospecific E2 elimination reactions. It's very important here to understand that the hydrogen and the bromine must be anti-coplanar, meaning that the angle between bromine carbon and carbon hydrogen must be 180 degrees. That means that we need to either rotate the hydrogen in order to bring it in an anti-periplanar position, meaning that the hydrogen needs to come here, or we can do the same for the bromine. If we see the molecule from the perspective of the observer, we have the front carbon here and the back carbon here. If we draw the Newman projection, we see that we have a phenyl group in the front carbon that is down. We can draw that in the Newman projection. We have an ethyl group that we're going to put it on the top right. And we're going to also have a hydrogen on a dash, meaning that we're going to put it top left. While for the back carbon, we have a bromine group pointing up, a methyl group that is a wedge, meaning that we're going to put it back to the right, as well as a hydrogen that is on a dash, and we're going to put it back on the left. It's very important here to note that the bromine and the hydrogen must be anti-periplanar in order for the elimination to occur. So what we can do is highlight the front carbon, and this will give us a better view of the back carbon. As far as we have to bring this hydrogen on the anti-coplanar position, this is the beta hydrogen, we simply need to rotate the front carbon in order for the hydrogen to come in the position of the phenyl. So if we rotate the front carbon keeping the back carbon stationary, the back carbon doesn't change, meaning that bromine, hydrogen and methyl will keep stationary, while we're going to rotate the back carbon, meaning that the hydrogen will come here and we're going to have a phenyl group up to the right and an ethyl group to the left. And here we can clearly see that the bromine and the hydrogen are in anti-periplanar configuration, meaning that the base will abstract this hydrogen, electrons will be transferred to form the double bond, and the bromine will live as a good living group. So in order to find now the configuration, you simply need to delete the bromine hydrogen, and this will give you directly what will be the substituents in the alkene. So if we delete those, in that case we will clearly see that we're gonna formate the alkene, and let's highlight now the front carbon. The front carbon we're gonna have an ethyl and a phenyl, and the back carbon we're gonna have a hydrogen and a methyl. So we simply need to draw the alkene, showing that one of the carbons will have the ethyl and the phenyl substituents, while the other carbon will have the hydrogen and the methyl. And we see here that the methyl and the phenyl will be close. So I need to draw the methyl from this direction to show that it is close to this phenyl group. This clearly shows me that I'm gonna have a Z alkene because methyl has higher priority than hydrogen for the left carbon, and phenyl has higher priority than the ethyl. In the second example, we're gonna see an E2 stereoselective elimination reaction. In the alkyl halide we have here, we can clearly see that we have one kind of beta hydrogens, and those are the CH2 hydrogens. Because the molecule is symmetric, we can omit one of those and we'll see the outcome only with one pair of CH2, because the molecule again is symmetric. We can clearly see from the beginning that the bromine of the alpha carbon is on a wedge and the hydrogen 2 of the beta carbon is on a dash, and this is the ideal position to have an E2 elimination reaction. However, for the H1 we need to rotate this to bring it in the position of H2. So let's go step by step and draw first a Newman projection that we'll clearly see. For the front carbon, we do have a methyl group pointing down. Hydrogen 1 is pointing up to the right because it's on a wedge. Hydrogen 2 pointing left, while for the back carbon I have an ethyl group pointing up, a bromine group pointing down to the right because it's on a wedge, and the hydrogen pointing back to the left. I can now clearly see that H2 and bromo are in anti-coplanar position. To bring now H1 in the position of H2, I simply need to rotate the front carbon. So I'm gonna rotate this counterclockwise. In that case, H1 will come here, H2 will come on the bottom, methyl group up to the right, while the back carbon will remain stationary. We can clearly see that in the second case that we rotated, H1 and bromo came to anti-coplanar position. To draw the alkenes now, we simply need to remove the eliminated hydrogen and the bromo group, and simply highlight the front carbon. This immediately will give us the substituents, where in the first case I'm going to have H1 and methyl for the front carbon, ethyl close to H1 and hydrogen for the back carbon, while in the second case I'm going to have methyl to the front carbon and H2, while for the back carbon I'm going to have an ethyl close to methyl and the hydrogen. This shows me that in the first case ethyl and methyl will be far away, while in the second case ethyl and methyl will be close. And this is why I get the major product for the substituents to be far away, while for the second product the substituents are close together.